How you doing?
Good.
Thanks for coming on my podcast.
Thanks for having me.
Yeah, I ordered your book. It hasn't arrived yet though, but I did manage to get a library download of it um, for the time being. But I also have The Evolution of Physics. You ever read that one?
No, who's that by?
That's Einstein
Oh, okay.
and Leopold Infeld.
Uh-huh.
Um, but I've also was looking at some of your papers. I think we could have a fun conversation. Basically, my idea was a couple months back, I had this criminal defense attorney on the podcast. She's a criminal defense attorney for the state of New Mexico. Why would I have a criminal defense attorney on an arts podcast? Uh, because she was passionate about what she was doing, and there was something about that episode where we were both just kind of geeking out about the most boring parts of the Constitution, like taxation or the fact that you can't board troops up in domestic homes and things like that. And I'm like, that was the funnest time I had. And so I'm trying to think outside the box about just kind of bringing people on who love their subject matter, but then also try to. I'm more inspired by people who are inspired, people who are passionate about what it is they're passionate about. And although the podcast is mostly rooted in the arts, it's slowly evolving because of this into an all subjects podcast.
Yeah, I was looking at some of I hadn't heard your name before, so I looked at some of your previous podcasts. And I was like, wow, he talks to everybody. He's got artists and lawyers, and it's just like it's a really interesting mix you've got there.
Yeah, and it's gonna go even further. Hopefully, my end game is to, of course, get to a point where like we are unpacking sort of the big questions of the universe, and I want to get panels of scientists and science fiction authors and futurists and go bigger. But I have to earn it, so I figured we could start with the standard standard model, um,
All
just
right.
just to create a foundation for this thing. But of course, being a filmmaker and a writer, and all of my undergrad and my graduate work was in creative writing. So you're definitely going to be the expert on this episode, which is what I prefer. Um, and I won't really 100% know where your expertise begins and ends. So like, I'll have a lot of questions as in and kind of if I'm trying to unpack something that doesn't fall into your comfort zone, just let me know.
Sure. Yeah, I have no problem saying I don't know. I know
Yeah,
college professors are famous for never saying those words, but I have no problem saying that. I say them all the time.
those are the ones I always got along with. Um, so, how long have you been interested in physics in general? Like, where did this start?
Well, it started really early, and the story I always tell is that I was reading a lot of science fiction back when I think this was maybe middle school or maybe even like fifth and sixth grade. I started reading a lot of science fiction, and I was reading this story that talked about these kids who built their own rocket ship, and they went to this other planet, which like they had to go through a hole in space to get there. And I'm trying to picture this in my mind, because that's the reason that we've never seen this planet, because it's beyond this hole in space that they had to go through. And so I asked my dad, is there such a thing as a hole in space? Can this really exist? And he said, well, maybe they're talking about black holes. And he gave me like a Scientific American magazine that had an article on black holes. So I'm like, wow, this is like science fiction, but it's really real. This stuff, they really think this is out there. So pretty much since then, I've just always wanted to study physics and learn more physics and, um, do what I can to advance the world of physics and our understanding of the world.
Yeah. I think science fiction for me has been my ingress into wanting to know more. I I think a lot about like wormhole and quantum tunneling theory, and as of late, I've been obsessed with the proton because I've become obsessed mostly with whether or not the proton will decay. You ever think
Proton decay is a big topic in physics. We all want to know whether the proton is going to decay.
what are your thoughts on that? Is that something that keeps you up?
Well, I wouldn't say it's something that keeps me up. At one time, back when I was, in sixth grade, I thought, oh, I'm going to solve all these great problems of physics. Now I know I'm never going to be the person who solves these things. So it's not something that I fret about, but I do find it fascinating. One of the things we know for sure about the universe is that there's a lot more matter than there's antimatter. And as far as the equations go, matter and antimatter look almost identical. They really look very similar in terms of the equations that we write about them. So if you've got this complete symmetry between matter and antimatter, why don't we end up with equal amounts, like a bunch of matter over here and a bunch of antimatter over there? And so why is the universe so one-sided in terms of the antimatter matter balance? And this was, the investigation into this started back, I think it was in the 70s by Andrei Sakharov, a Russian physicist. And what he realized was that there are three conditions that are necessary for you to end up with more matter than antimatter, and the imbalance of these things. So, one of them is a non-equilibrium situation. And the Big Bang is like the perfect non-equilibrium situation, right? Everything's expanding and, the temperature's dropping and it's extremely non-equilibrium. So that's fine, we've got that. And then another one is the proton, not specifically a proton, but there has to be a violation of the symmetry between particles and antiparticles somewhere in the equations. So basically what that means is we expect that there has to be a proton decay at some level, because otherwise we wouldn't end up with this matter-antimatter imbalance. So, so everybody's waiting to see a proton decay, and they've built these massive experiments where they're looking at lots of protons at the same time, and nobody's seen it yet. So it's still a mystery. We don't know why we haven't seen it, because it seems like there must be there. But you have to do the experiment, right? You can't move on until you've seen it.
How might they do these experiments? Like, what is the mechanics in the first place of observing a proton?
So one of the ways they do this is the proton lifetime is like longer than the age of the universe, right? We know that. So you can't grab one proton and sit there and wait for it to decay, right?
Right.
You're not going to see it. So what you do is you get a whole lot of protons, right? You get a whole lot of protons in a big container of some sort, and then you put in a bunch of detectors and you watch to see if there's any evidence of a proton decay. So what they do is they use these huge tanks, and sometimes they just fill them with water, like super pure water. Other times they use something that's like a cleaning fluid. It's got a chlorine atom in it because chlorine is good for some reason. And then what you look for is if the proton decays, it's going to emit some energy, and that energy, under the right circumstances, gets converted into light, and then you can basically see that light. You can watch for the light from those emissions. So they have these huge tanks, and they put photomultiplier tubes all up and down the sides. You can, if you Google it, you'll find some photos of the interior of these things. It's really incredible what they look like.
Yeah, I saw one setup. It was under like a mountain in Japan. I don't know if it was for like looking at protons, but they were. I think they were like studying neutrinos.
Neutrinos, yeah.
And it was just like all these tanks, and I guess the water was so pure that it was capable of corroding metal. Like I don't remember the specific reason for that, but in the write-up about it, it was talking about how the water inside it was so pure that it would like destroy your insides or something like that. I don't know the logic of that whatsoever, but
yeah, that sound quite right to me. But it is a problem. I mean, if you want really pure water, what do you put it inside of? Because anything you put it inside of, it's going to dissolve little bits of the thing that it's in, right?
Yeah.
And then it's not pure anymore. So it's really hard to to maintain the purity of that water.
Yeah, that's half the problem with a lot of content I've found these days is without citation. It's really hard to understand what these guys mean. The way they wrote it up gave me that picture. They might have been meanings. They might have meant something else. I don't know.
Right. Yeah. Yeah, and I found that surprisingly. I found that even with a lot of science journalists at respected publications, they don't necessarily explain, at least the way I understood it when I went and looked at the original article, and they don't even necessarily link the original article on online articles, which to me is kind of incomprehensible. It's so easy to put a hyperlink in there and say, here's the Nature article, or here's the physics article that we're talking about, and then people can go look at it for themselves.
Yeah, let's see here. I had a whole bunch of notes about the proton before we get off the proton. I have this statement here. Protons have a mass of 1, which is the same as the relative mass of neutrons. What is a relative mass of neutrons? What does that mean? Trying to understand some of the language.
Yeah, I'm not sure what that is intended to mean. I think the statement is just that the mass of the proton and mass of the neutron are very close. They're very close in mass. Whereas the electron is a whole lot later. It's like 1,000 times later.
Gotcha. All right. Can we talk about quarks for a sec?
Sure.
What are they? So I know that like the atoms are made of quarks, right?
So yeah, so atoms are made of protons and neutrons, right? With electrons sort of in a cloud around them. Mm-hmm. And each proton is made of 3 quarks, and each neutron is made of 3 quarks.
So what is the quark though? What is it been like? I don't know I don't know. I'm trying to get a picture of what it is and how it might have been identified, how it might be handled. Is it something that can be handled?
Yeah, so that's part of the problem with quarks, is that up until the quark, all of the particles that physicists had proposed to exist were particles that you could actually detect in some way. They had an electric charge, so you could detect them with a charge detector, or they interacted with some other particle so that you could see them when they bounced off of something else. But the quarks, we believe, are never knocked free. No matter how hard you smash something into a proton, you never knock one of those quarks free. So if you can't see the quark all by itself, then how do you determine whether it has the properties that you think it has? Well, basically, the trick is to just smash stuff through the proton so fast that you're effectively seeing just one quark of all the junk that's in there. Because even though we say that the proton is made up of just 3 quarks. The 3 quarks are actually bound together by all these virtual particles that are constantly popping in and out of existence. So, so there's a lot of stuff going on inside a proton. But basically, if you smash something through it really fast, then you can look for the characteristics of a particle that has 1/3 of an electron charge, right? So all the other particles we know of, all the free particles we've ever seen, have like an electron charge or the negative of an electron charge or some multiple of that, right? Twice the electron charge or 4 times the electron charge. So charge is quantized like that. But the quarks are supposed to have 1/3 of an electron charge, which, that was a pretty radical idea at the time, that anything could have anything other than a whole number of an electron charge. But that's basically the way that we've determined the properties of these quarks, is by doing these high energy scattering experiments where you're essentially peering inside the proton with these high energy beams of particles.
Are these kinds of the mechanics of these, are these able to be done in regular lab settings, or do you need like the collider to do something?
Yeah, you need the biggest collider you can get, right? So that's why physicists keep asking for bigger and bigger colliders. We want a CERN, we want a Stanford Linear Accelerator, we want superconducting super collider, which never got built, but
someday, hopefully. Now that we've got science on board, the executive branch.
Right.
Is the European one still the biggest one?
Yes, CERN has the highest energy.
What would it take to like get some time on that? Like, would you be able to apply for time on that? And
I would not. I'm not an experimentalist at all. I'm a theorist. So yeah, and that answers the other part of your question. I don't know. I don't know what it takes.
Yeah.
I think basically, if you're working with other people who are working at CERN, that's kind of how you get in. It's like, oh, well, why don't you come join our research group for this next experiment, and then you're in.
Would it make sense for there to be a sort of, not say publicly available, but available in general to qualified academics, a collider that's big enough for these experiments so that people who aren't affiliated with a specific organization can just apply to use it? I feel like that would advance our understanding of this stuff exponentially.
Yeah, I don't know. I know what they are doing nowadays is they're making all the data publicly available. So if you want data from CERN, you've been watching the A0 experiment at CERN, and boy, that's really interesting. I would love to get my hands on that data. You can go and ask for it. You can say, I want to analyze that data in a certain way, and they'll give it to you. That in some ways is even better than making the collider itself publicly available, because they're cranking out these masses and masses of data all the time, and so if you know how to look for something in that data, you can do it.
Have you ever sent them a request for documentation?
I haven't. No.
I'm always interested in like the mechanics of functioning in a part of the world that I have no business in. I'm super nosy like that. You have I pulled up your list of classes. You have a lot of classes that I would love to be a fly on the wall in, like Quarks to Strings.
Quarks to Strings I actually created partly based on my book. That was, in fact, it was the chair of the department who suggested it to me. He was reading my book. He said, you should start a course based on this. And I was reading a lot of philosophy of science at the time. So I said, well, I don't think my book by itself really makes a course, but maybe if I bring in some of this philosophy stuff, which scientists never really talk about. We don't talk about what it means to know something, or or how is science different from normal knowledge, or is it different from normal knowledge? So a lot of these really sort of interesting philosophical questions, and push my students to think about what does it mean to prove a theory. We don't prove it the way you prove something in mathematics, where it's like this completely airtight logical sequence of steps. You have to get evidence for it. But once you've got evidence, there are other possible explanations of that evidence, right? So how do you know when something has been established to the point where we say, okay, we believe that now. We believe general relativity is true, or we believe the standard model is true.
How often are you using the mathematical language in your work?
Well, like I mentioned, I'm not involved in research these days. I'm just teaching my courses and doing some writing. So I don't, I don't work on those things today. But the mathematical language is crucial to theoretical physics. I mean, everything I wrote when I was doing theoretical physics was written in a very mathematical language. And in fact, you almost don't need words at all. You can just kind of throw the equations down there. You can read papers that are written in a language that you don't know and say, oh, I see what they're doing. I recognize that's supersymmetry, or something like that.
How is it that sometimes I read about how physicists engaged in research are able to make a prediction based on the language or an assumption. So like, let's say they've got this equation and they figured out how a black hole functions before they've been able to observe how a black hole functions. Mm-hmm. How is this the language? I don't understand how the language informs them of that answer before they've had a chance. Because for me, the scientific method was always sit down, observe, document, observe.
And then draw your equations from the phenomena, not the other way around.
Yeah.
Right? Well, I mean, you can think of a very simple situation. I mean, you're at a baseball game, right? And if somebody hits the baseball, if you know what direction it's moving and how fast it's moving, you can predict where it's going to be, right? And in fact, the baseball players do that without any equations very automatically, right? They know how to track where that baseball is going to be. But we do it with math. And, the math says, here's the path that it's going to follow, and there's the mathematical expression for it. So you can say, oh, okay, it's going to land here, and it's going to land, 50 yards away or whatever. So the black hole properties are sort of a more sophisticated version of that. You say, well, okay, now I've got a mathematical description of what a black hole is. Now let me see if I can generalize that description if there's like a big cloud of gas around it. So the gas is going to start swirling in like water down a toilet, and as it swirls in, it's going to heat up. And if I can figure out the rate that that's happening, then I can figure out how hot it's going to get and what it's going to look like when I look at it through a telescope. And so you can make these kind of predictions. And then go ahead and point your telescope at it and see if that's what it actually looks like. So that's the way we use the equations predictively rather than just descriptively.
Yeah, that makes sense. This is good. Part of this is defending science. I see that you have on this page. I don't remember what this page was on its purpose on the website. It just happened to be like a list of classes that you were involved in, plus some documentation provided. So you have like a PowerPoint called My String Talk. Was that your PowerPoint?
Yes, I assume so. If it was on my webpage, I haven't used that webpage in a long time, so I'm not sure what's on it anymore. But I did give a talk on strings at one point. Just, I think, because some people in the department were interested in hearing a little bit about strings that I know. I'm not a string expert by any means, but I do know a little bit from my
graduate. One thing that I was interested in it, I'm a really big defender of science above all other ways of life, I guess, well, except maybe the art life. But you have this article, Does Life on Earth Violate the Second Law of Thermodynamics? And it's under a section called The Theory of Evolution is Still Under Attack from Several People with a Religious Agenda. And you also included a link, or whoever did this website also included a link to an article called More Intelligent Comment on Intelligent Design. And I'd love to unpack this subject a little bit, because I think that we may agree on a variety of issues within this. How about the paper you authored? Does life on Earth violate the second law of thermodynamics?
Right. So if you get into, and you got to realize this was sort of back near the beginning of the internet, when you could go online and argue with whoever you felt like arguing with. And I was sort of attracted to these people who were claiming that that evolution itself refutes or physics refutes evolution, or evolution refutes physics, or these creationist arguments, basically. I just was trying to point out that these arguments just don't hold water. And when you see a lot of those creationist arguments, you don't ever see them messing about with equations or plugging in numbers or anything like that. They'll just make some blanket statement. Oh, well, evolution violates the laws of thermodynamics. Well, there's a whole host of reasons why that is not true. And I, being a physicist, wanted to point to one of the physics reasons that happens not to be true. But you'll see these things out there as if this is something that's been proven, and it just seems like there needed to be a voice out there talking about these things in a more precise way and showing why it's wrong.
Yeah, I think the worst for me is, or the worst to me is, when they bastardize perfectly legitimate information that gives you an obvious answer that's not in line with what they're preaching, but they say, well, here's why it's in line.
Right.
I hate that bastardization of information. I really enjoyed this paper, actually, and I'm going to link to it in the description, along with every other thing that I'm referencing, just so that everybody can follow the conversation. I don't always explain everything in these podcasts. I just kind of start them. I didn't even introduce you, but I'll introduce you in the description so that everybody knows. But I think philosophy should be a bigger part of all this. I think it makes a lot of sense.
Yeah, I think that's true. And the physicists have kind of stumbled into this area where they're starting to trip over philosophical questions. And the string theorists in particular, they started talking about string theory as this was the theory of everything, right? Not the theory of almost everything, the theory of everything. String theory was going to be the one theory that explains all the properties of the particles and all the properties of the universe, and anything that you wanted from physics you could get out of string theory. And as they just explored string theory more and more, they found that it's really not just a single theory. It's really this whole class of theory. In fact, it's an enormously large class of theories. And at first there was this hope, well, out of this huge class of theories, string theory itself is going to narrow it down, right? There's some, sort of like the lowest energy theory or something like that, the bottom theory that is more fundamental than all the other theories. And that would be the one. And then they kind of gave up on that. And so then they were sort of in this weird space where they're saying, well, we still think string theory is the answer, but we know there's lots of string theories. And so maybe there's just some process that goes on creating universes with all the possible string theories as their basic physics, right? So that's why string theory is still truly the fundamental theory. So they just kind of wandered down this path of not wanting, hanging on to string theory and not wanting to give up on it. And so they changed the whole philosophy of, well, we're not trying to predict what's in the universe, right? We're just trying to explore this wonderful multiverse of string theories. There's been some pushback against that from some people. And I'm not sure, not being in the string theory community at all anymore, I don't know to what extent that that kind of philosophy has taken over. But it was really startling to hear theoretical physicists starting to say things like, well, physics is not really intended to be predictive. It's not really intended to describe the universe, right? It has this other goal of describing all possible universes.
I feel like that's more of a thought experiment than an actual, I don't know. The idea of a multiverse, and until we can prove it, it's really just a thought experiment. And I don't even know how you would scientifically navigate towards making that a part of an acceptable model beyond just, it's a cool idea. Like, I love thinking about it, but it's not really that accessible.
Yeah, and yet people have tried to build it into an actual model. They've tried to create structures that do this, that have this branching kind of effect where different little baby universes bubble off constantly, and so you get all these different realms of the multiverse that each has its own set of laws of physics. But that's not something I'm really on, so I can't explain it any better than that.
Yeah, that's cool. Are there aspects of the standard model that mystify you, even to this day?
Yes, there definitely are. I mean, some of them are questions within the standard model itself. So like we talked about how quarks can't be kicked out of the proton. That's what we call quark confinement. And I talked a little bit in the book about why we think that the quarks are confined, that there's something in the theory that tells us those forces get stronger the more you pull on the quarks. And so, if you had to pull them infinitely far apart, you would need an infinite amount of energy and that kind of thing. That has never been mathematically proven. That quark confinement is one of the big outstanding issues in the standard model. And in fact, it was named, I think it was back around the turn of the millennium, somebody came up with these prizes, these Clay Millennium Prize, it's called. And I don't remember how many, 5 or 10 mathematical problems that he named as, and it wasn't just one guy, I think he had a committee to pick the problems as like the problems to be solved in the next century or millennium or whatever. And this was one of them, the quark confinement problem. It's considered like one of the outstanding problems, not just of physics, but of mathematics. But then we have these hints in the data of things that don't quite fit in the standard model. And one of them we're pretty sure about now is neutrino masses. We've seen evidence that neutrinos have mass, whereas in the basic standard model, they're massless. They have strictly zero mass. And there are ways you can mess around with the standard model to give them masses. But it's sort of, it's not the obvious thing to do. And it's sort of hinting that there's something beyond the standard model that we don't know about, that we really need to know about to understand why they have masses. So neutrino mass is another one. And and then there's an issue with the spin of the muon, which doesn't seem quite right compared to what the standard model predicts. And so there are these little puzzles that are hinting that the standard model isn't the whole story. There's more to it than we know.
So, what? Let me just think for a sec. Is this the standard model? What would it take to integrate? So, the standard model says that neutrons have no mass, or neutrinos have no mass.
Neutrinos have no mass,
but they do have mass.
But we now know experimentally that they have mass, or we think they do. I can go into details, but you probably don't want to know.
Well, I just maybe we can, but for now I'm trying to figure out why is it that this accepted model, like what would it take to make it a part of the model? Is it just a matter of retooling the math that's used, or is it some kind of like who says that this is the standard model? Like, let's say the neutrinos is one thing and the muon is the other thing. Maybe in a year they come up with 10, 20 other things that doesn't really conform to this model. At what point does the model not the model? Like, does that make sense?
Right. Yeah. So you can take your model and you can push on it. You can you can add stuff to your model, and then then it wouldn't, strictly speaking, be the standard model, but we'd still basically consider it the standard model. And then the other way you can do it is to create some bigger model and then say, oh, look, the standard model sits inside of this model in a nice, neat way. But the bigger model predicts other stuff that's not predicted by the standard model. So basically for the neutrinos right now, what people are doing is the first method. They're saying, oh, well, we can give the neutrinos masses if we add, this kind of structure to the mathematics, or often what they have to do to give them masses is to introduce a bunch of really heavy neutrinos. Like for each neutrino, there's a partner that's a neutrinos are very light, right? They're tiny masses, but these partners would have really large masses, and that would explain why we haven't seen them, because they have such big masses that we haven't been able to produce them in a laboratory. But it also allows us to write a mathematical structure that gives the neutrinos their tiny masses. So do you just kind of stick it in there by hand? Well, that's what people are doing nowadays, to just so they have something that they can work with and test against experiment. Okay, well, here's the basic thing that we can add to the standard model that makes this work. But then, and this goes all the way back to the 70s and 80s when I was in grad school. What they call grand unified theories, where they have a bigger model, a bigger symmetry structure. And then in some of those, there's something called a seesaw mechanism that takes the neutrinos and it pushes one neutrino up in mass and the other neutrino down in mass, so that you get exactly that kind of, one very heavy one and one very light one that we were just putting in by hand before. So yeah, and in that case, you wouldn't call it the standard model, right? Now it's a grand unified theory. Now it's a SU5 model or O10 model or something like that. They all have names of these mathematical groups that describe the symmetry structure.
What is the what would it take for a shift in sort of defining the model? I guess be like, what would
right. So
like?
We would want to see something else that's predicted by the model show up at a collider experiment, right? That's the basic bottom line. If it predicts a particular particle and you go out and you see that in your collider, then okay, now we've got a new model. This one seems more accurate than the standard model. That's what everybody thought was going to happen at CERN. That's what everybody thought was going to happen when we found the Higgs. We would find a whole bunch of other particles, and we would be able to say, oh, those particles are the particles that belong to the model blah, right? This is the one now that we can use to replace the standard model. That didn't happen. We found the Higgs and nothing else. So that was kind of a shocker. That's before the Higgs was found, they referring to that as the nightmare scenario. They said, if we just find a Higgs and nothing else, that's a nightmare scenario, because then we don't know what to do, right? None of our models are working. So that's kind of where we've been for the last, 10 years now.
Well, cracking the universe isn't supposed to be easy.
It's not supposed to be easy, right?
I appreciate you answering all my questions. I feel like it's good, though, to have an outsider kind of asking some of these questions, because there's so much content out there with people who know what they're talking about, and it's easy to get lost.
Oh, yeah.
So it was important to me to be on the side that kind of loves the thought experiment of all this, but doesn't 100% understand it. And so that's kind of why I'm asking about the mechanics of it, and sort of, I guess, in some cases, the politics of science, too. There's an aspect of that, I think.
Yeah.
Is it possible for someone to observe an atom outside of a lab? Like, let's say my nephew, who's 1,000 times smarter than me, wanted to set up an experiment in his garage. Is there a way for him to observe an atom? Or does that require like special infrastructure?
Well, I think the answer is going to depend to some extent on what you mean by observe. How exactly are you going to observe it? You definitely can't go out and buy a microscope that's powerful enough to see an atom, right? It's not happening. I think what I would call the most direct observation of atoms that I've ever seen images of are where they use these things called a scanning tunneling microscope, where they have a sharp tip, and they move it across the surface, and they can actually scan the height of the surface, and you can see individual bumps that are like the individual atoms in some of these. It looks like a photograph when you look at it online. Of course, it's not a photograph, but it's reproduced from the data they got from the scanning data. But it's pretty cool. You can actually see those individual little lumps of atoms, or a ripple where there's regularly spaced atoms. And no, I don't think you can build that. Well, I guess if you got deep enough pockets, you could buy one for your garage, right? But it's not a super collider. It doesn't need miles and miles, but it does need a fair amount of space and a lot of money to get one of those.
Yeah, I bet. Is there like a finite amount of, like, are there specific universities or organizations that would have those?
Yeah, honestly, I don't know how common they are. It's not, like I said, it's not a super collider. It's not something where there's only one or two in the world. I'd say there are probably, hundreds, if not thousands, of these things in the United States. So, yeah, call up your local university and see if you can find somebody who has a scanning tunneling microscope.
There's got to be at least one in New York. Do you think you'll ever find your way back to the lab, to just practicing?
Writing papers? Probably not. I've kind of thought that, well, once I retire, maybe I'll try to catch up on some of these areas. But I do feel like I don't have the concentration that I did when I was 20 something. It's not easy to jump into an area where you've been out of it for 20 years. I think what's more likely is that I might try to do some writing in these areas of philosophy of science, philosophy of physics. I've gotten really interested in the philosophical side of things, which I guess is kind of a cliche for theoretical physicists. When we get old, we turn into philosophers.
I'd love to read some of that, though. When you publish, keep me in the loop.
Yeah, and I think, like quantum mechanics is a mess. We still don't understand quantum mechanics after 100 years. So, I mean, not that I'm likely to solve that problem, but it's just such a fascinating area. And it's one of these places where philosophy and physics overlap. Yeah. So I'd like to, see more what other people are writing about it. I haven't been keeping up on it much because of all the courses that I have to teach, but it's fascinating stuff. So if I had more time, I would definitely be reading more of that stuff.
Yeah, quantum mechanics is super spooky, and eventually I'll probably have some episodes about that more, because I've been thinking a lot about like the double slit experiment and all that, like the superpositions, but not quite there. I'm not ready for an episode on that yet. And so far, the only people who are really talking to me about it are science fiction writers, and unfortunately, a lot of that is not really. I mean, they're intellectual thought experiments, but they're not really able to unpack sort of the mechanics of how all of it is known, I guess, which is. I don't know if you figured it out, but I'm really into the nitty gritty of how do we know any of this? So.
Well, I'll be happy to come back and talk to you again if you want to talk about quantum theory and superposition and stuff.
Yeah, and if you ever want to just hop on and say, hey, I read this book, let's unpack it, that could be a great episode too. So, anything.
Sure.
I promise we'll wrap this up soon. But with teaching, are there, for you, have there been surprises for you in regards to like, well, I never thought I'd get this out of teaching? Because I've interviewed some people who've segued into academia from the creative world, and they ended up getting more from teaching than they did when they were publishing books or making films and stuff. I was just wondering what your experience is with that.
Well, I definitely can say that, even after all the years I've been teaching, and even just staying with introductory physics, first semester and second semester physics, which is what I mainly teach, that students still come up with questions that I don't know the answer to, and sometimes have surprising answers when I do try to look into it, or I find that, oh yeah, that sounded like a simple question, but it's a really complicated answer, and I don't understand what they're telling me. So yeah, I get those kinds of things. I think the other surprise for me has been, when I thought about potentially being a academic, like back in grad school, and saying, okay, well, what am I going to do with this? What's my job going to be? What's my career going to be? I kind of always pictured myself like at a small liberal arts college where I had all these really smart students and I could really push them hard and give them all this complicated physics. And instead I'm at, a state school, which is sort of not even the top tier state school, but like a lower tier state school. And a lot of my students are not really on top of stuff. It's a real struggle for them to understand. So it's been a struggle for me to address that population, to try to find ways to communicate with students who are not the ones who got straight A's in high school. These are the ones who are struggling with some of the concepts and are struggling with the mathematics. And how do I revise my teaching to reach them and to make stuff accessible to them. So that's been a real challenge. I just sort of had to change my mindset to think about, oh, well, my challenge now is not explaining really complicated stuff. It's explaining it's simple stuff, really basic stuff, but in a more understandable way.
Are the ones that struggle with it the most? So is there a correlation between the students who might be taking it as a general education requirement versus those where the science class falls into their degree plan?
Yeah, we actually have several different intro physics classes. I mean, we have one for sort of non-science majors, and then we have one that is mostly for the biology and pre-med type students. And then we have the one that's calculus-based, and that's required for engineering students, physics majors, chemistry, I think. So we have these different tracks depending on what their major is. So it's not like I have all those people together. And I mostly teach the calculus-based physics.
I hope you really go into the writing about the philosophy side of this. I would love to digest some of that, and whether or not you publish, I'd like to have you back on as well. I think that you're fun.
Great. Well, it's been a pleasure. I really appreciate. I mean, I was so flattered when I got your email that, boy, somebody wants me to talk to them about physics. And as you can tell, I just love talking about physics. So yeah, I'd be happy to do it again.
Hey everyone, thanks for visiting my YouTube channel. Don't forget to subscribe and hit that bell notification.